Are you tired of slow, gimmicky, and memory inefficient sorting algorithms? Does the worst case performance of quicksort scare you off? Do you want to make full usage of your multi-threaded CPU? Well, then I've got an algorithm for you. Merge sort was invented in 1945 by John von Neumann, known by many as the smartest polymath in the 20th century. The design of the algorithm follows the divide and conquer paradigm. Split the problem into tasks so simple that they become trivial to solve. This allows the algorithm to achieve a time complexity of big O n times log n, even under the worst cases. But before I show you the main algorithm, I first want to explain one subroutine that plays a major role in the process of it all, that being the merging method. This function takes in two sorted arrays as input and merges it into one sorted array in linear time. Here's what it looks like. So you're given two arrays and you have to merge them into one. The two arrows represent two variables that indicate the position in each array. Each step, you copy over the lowest value out of the two arrows. In this case, it's 1. And then you increment the arrow. Between 3 and 2, the lowest is 2, so you copy it over and move the arrow. 3 and 4, it's 3, so you do the same thing. And you keep repeating this process until one array is empty. In which case you just copy the rest over. The entire procedure consists of 3 simple steps. Step 1 is splitting your list into 2. Don't worry if your list has an odd length. One slice can be longer than the other. Also, if your list has a length 1, it's already sorted. You're done. Step 2 is performing this algorithm on your 2 new slices. Step 3 is merging your now sorted slices together with the merge method. That's it. Now, I see the confused looks on your faces, so I'll try and explain why the algorithm actually works. Every split of the array is half the length of the original. Eventually, you're going to be splitting them into arrays of length 1. The trick that makes this algorithm work is that lists of length 1 are already sorted. This is the base case of the recursion. Still don't believe me? Here's the code. In my main method, I create, sort, and print an array. The merge sort method is the function that partitions, sorts, and merges 2 array halves. The base case occurs when the array has a length of 1 and does not need to split anymore. I use Java's built-in functions to cut the array in half. The function is also clearly recursive, as it calls itself twice, making a tree-like structure. Here's the merge method that I was demonstrating before. A index and B index represent the arrows, indicating the position in the array. The first 2 if blocks check if either array is completed. If that's the case, the for loop will keep on looping and copying the other one over. Otherwise, it'll take the lowest value out of the 2 arrays, increment the index, and that'll be that. Once the loop has finished, the merging is complete. And as you can see, it works. At this point, you may have seen this diagram and thought, what makes the top layer different from the middle? Why can't you just start in the middle? Well, the answer is that you can. This is called a bottoms-up merge sort, where instead of recursion, loops are used. The reason we use recursion in the first place, though, is because it provides a neat and tidy framework for merging the lists back together. Although merge sort is a great sorting algorithm generally, there can be some situations where you may want to avoid using it. One such case would be on a system with limited memory. This is because merge sort requires at least a copy of the original array to be made, which can hog resources. Another situation would be sending a list that's already sorted. Some algorithms, like bubble sort, will, if given a sorted list, simply iterate through it and send it back. This is not the case for merge sort, however. In its default implementation, the entire process of splitting and merging will take place. To address some issues, many variations and optimizations have been made to this algorithm. One of them is called the natural merge sort. In this variation, Sublists of ordered numbers that already exist inside the array are scanned for and collected to avoid having to sort them again. The ping pong variation, also known as quad merge, merges 4 lists at a time instead of 2 to minimize the number of times the lists have to be copied. Now here's some fun facts about merge sort. It's very efficient when used on tape drives. This is due to the way they access and write data. It's also used by the Linux kernel for sorting linked lists. Lastly, it's very parallelizable due to its recursive branching nature. Now, I'll leave you with a problem to think about. In my code, I made new arrays whenever I wanted to, which is memory inefficient. I challenge you to implement this algorithm where you're only allowed 1 copy of the original array in your code. Thank you for listening.